Hi, I am Paromita Dubey, an assistant professor in the Data Sciences and Operations Department at USC Marshall. In the last decade, we have seen groundbreaking advances in big data analytics. Tools and techniques for handling massive data sets have evolved, allowing us to tackle problems that would have been impossible a few years ago. But recently, the data we collect has become more and more intricate. Data like fMRI images, social networks, and n-grams have become routine in modern data science. When a practitioner starts to analyze data, it is typically presented in the form of a table. And adding the rows of the table or multiplying them by a number are actions one does not think twice about. But what happens when the data isn't in a simple tabular format? What if it's more complicated? Say images, networks, or curves. This creates challenges for many real-life statistical tasks. For example, in scenarios when scientists might be interested to study connections between brain networks and the gut microbiome. Today, I'm excited to share with you how one could extend traditional data analysis methods to deal with more complex data forms in a model-free and a geometry-aware way. Complex big data can be found in many fields like business, economics, climate studies, social sciences, and health analytics. Often represented as matrices, curves, histograms, or images, known as non-Euclidean or object data, this data does not admit standard math operations. Our solution? Focusing on the distances between the data points in an abstract space rather than the data itself. These distances measure how far apart the different data points are. Using probability theory, we have shown that the relationships in such numerous data sets can be understood by studying the distribution of these distances, which uniquely characterize the underlying data structure. We have named the collection of these distance distributions as distance profiles. These distance profiles allow us to analyze non-Euclidean data, solving the problem of what to do with all this complex big data and answer questions that traditional methods can't. Equally important, these distance profiles are easy to compute, providing a theory-backed practical toolkit for analyzing complex object data. Ranking complex data is an important question that appears in many data science applications, including search engines and recommendation systems. Why is ranking data important? Because ranks give important scores to data points. Intuitively, data points that are in the center of a data cloud tend to be closer to other points, while those on the edges are further away. We have developed a new ranking system for complex data called transport ranks, based on statistical optimal transport to compare distance profiles and how observations stand with respect to each other. These ranks use only the distances between the data points to assign a score, indicating how central each point is within the data set. A lower rank means a point is less central, and very low ranks can help identify outliers in the data. With this approach, we can create new visualizations, like showing the center outward patterns for object data. In this example, the left plot shows curve-valued data points for different countries, where each curve is a country's age-at-death distribution, and the right plot gives their transport ranks, showing the center outward patterns. In another example, we ranked the energy compositions of the United States, which are simplex valued data, using the transport ranks to show which states are more typical and which are more outlying. This new concept opens the door to apply traditional rank-based statistical methods to non-Euclidean data, creating a rich set of options for analyzing these very complex data sets. Often, Practitioners look for reliable tools to address questions such as whether two populations differ, if there are abrupt shifts in the data distribution, or whether variables are independent, where all of these conclusions can be drawn with statistical significance. We have developed new methods for comparing groups of complex data using our distance profiles. We can test whether the networks underlying brain images of healthy aged individuals are different from those of Alzheimer's disease patients, based solely on the distances between these networks. Here, the p-values obtained using our method gives the confidence to draw statistical conclusions to identify these differences and to detect whether brain connectivity networks change with increasing age. We have also expanded this approach to detect sudden shifts in the data generation, known as change points with guaranteed accuracy. The p-values that we produce using our method is what gives us the confidence to say that there are significant change points in US electricity compositions around June 2007, March 2015 and March 2019. We have also used this to find shifts in the compositions of movie genres released each year on IMDb. Additionally, we created a test to see if two data objects are related. For example, whether people's social network activity is linked to their physical activity. Even though our methods work only with distances, they tend to work very well, not just for complex data, but also for regular data sets, showing strong and reliable results in all cases. By focusing on distances between the data rather than the data itself, we have developed a key to help unlock the analysis of complex non-Euclidean data. From ranking data points to detecting changes in business environment, to comparing populations and identifying relationships, distance profiles allow us to perform a wide range of statistical tasks when traditional methods fall short, opening new possibilities for data analysis on this ever-growing and more complex data generated by our modern world.